All right. Good morning, everyone. Happy to be with you this morning. My name is Mathieu Planche. I've been a CEO at Witbe for the last 7 years. And in case you haven't noticed, from my French accent, I am French. I've been living in SF for the last few years, and I couldn't shake it. And so, true to our French fashion statement, I am wearing the same shirt as on my headshot, and no, I did not do it on purpose, though when I realized I didn't change my shirt. Today we're going to talk about a passionate topic in our industry, the silent war that is raging between social networks and operators as to the bandwidth that the social networks are using to send these short-form videos on our phones. But before that, I wanted to say a quick word about Witbe, just so you understand how we collected the KPIs that we will discuss today. At Witbe, we specialize in test automation and monitoring of any kind of video service, and our uniqueness is that we do it on real devices that we connect to our Witbox, which is going to run automated tests autonomously and measure a bunch of KPIs by directly looking at the screen of the devices. And so, depending on the customer that we work with, we can have a look at the video availability, audio availability of channels. We can have a look at availability of assets on VOD platforms, and we can also have a look at how social networks are streaming videos in the short-form format on any type of iOS or Android device. Most of the time, our customers purchase our products in order to understand how they deliver, to understand the quality of experience they deliver to the end users. But sometimes we also use our own products in order to publish some studies about challenges in the industry. Last week, we ran an analysis of the Super Bowl, and then it's not the topic of the discussion today, but I'll send you to witbe.net if you want to have a look at it. Very exciting results in terms of low latency streaming for OTT platforms. The topic of the discussion today, again, is short forms videos and how they're streamed on social network apps through different networks. So let's have a look quickly at the methodology that we used. We had a couple of Pixel 6 devices connected to our mobile robots that you see here. We tested 5 different networks, AT&T, T-Mobile, and Verizon for the kind of traditional mobile networks. We also selected Boost Mobile, which is MVNO, and also Wi-Fi. And we tested 4 different apps, Instagram, TikTok, YouTube Shorts, and Facebook. And so we ran the test sequentially. For each network, we ran 200 scenarios, 200 runs. And in each scenario, the Witbox looked at 50 reels. So that's 10,000 short-form videos per operator, or 50,000 videos. And so if you have kids or partners that are scared to be addicted to short-form videos, like my wife, for instance, it can be worse. Our robots can be much more addicted to it. Out of all these sessions, we looked at a lot of visual KPIs. How fast did the different apps launched, and if they were available to launch or not. And through the scrolling sessions, we looked at visual KPIs, the initial buffering time for each reel, for each short-form video, but also during the short-form video, the 10 seconds playback, we looked at rebuffering events, frozen screens, high blurriness, blockiness, these kind of visual KPIs that impact the user experience. Something new that we added from the session we had done here 2 years ago is data tonnage KPIs. We also performed a network trace on the device in order to get more network analytics on what happened during the sessions. And this allowed us to get the amount of data that was downloaded by the device and get a throughput, like average throughput from this. And so let's have a look at that throughput, which is a good estimate. It's a good estimate of how much data the different devices are burning when they do these viewing sessions. So here you see we have every application, so Facebook, Instagram, TikTok, YouTube, split across the 5 different networks that we had a look at. And so if we look at the results and we look at one application at a time to get a clearer view, we can see from here that the different apps have different strategies based on which network they are connected to. If we look at TikTok, for instance, we were surprised to see that TikTok behaves basically the same across all operators. There is no major difference in throughput, whether TikTok is connected whether the phone is connected to a mobile operator, or MVNO, or Wi-Fi, which was surprising because our a priori results guesstimate was that apps would consume more data on Wi-Fi, which is the case for Facebook, for instance. Facebook consumes on average 1.2 megabit per second on T-Mobile, and more than twice that on Wi-Fi. So here we can see that Facebook has a strategy where it's shaping the quality of the videos that they stream on the different devices in order to consume less on mobile networks compared to Wi-Fi. What's interesting also is that we did not measure the same behavior for Instagram, which also belongs to Meta. Instagram behaved much more like TikTok, with an average throughput that was about the same across the different networks, to the exception of Boost Mobile, where the average throughput was significantly lower, half. And so this makes us imagine that there is maybe like a peering or an agreement between Meta and Boost that is not here, and so they're trying to to put less strain on the network. So these are kind of like the overall results that we got. So from here we can already see that the different networks, the different social networks, behave very differently compared to when you compare them on how they when you compare them on the different networks. Different strategies are put in place, and it's interesting to see that they don't always. They are experimenting on how to consume less data in order to send these short form videos. We then had a couple of deep dive analysis on a couple of specific KPIs. We first had a look at app launch time. When we looked at Facebook, it was very interesting to see that Facebook does not behave the same at all on the different on the different networks. It's very stable. The app launch time is very stable on Wi-Fi and T-Mobile network, but we saw a lot of variability on AT&T, Verizon, and Boost. This is what it looks like. You can see it loaded in about 2 seconds on the right on T-Mobile, and about 4 seconds on Verizon on the left. And so we had a look at the network trace in order to see if there were some hints as to why this was happening. On Verizon, we detected that during the initial launch of the application, we had several SYN packets that were sent that did not receive a response. And shortly after, we observed some TCP/RST response packets where a retransmission was necessary. This behavior was not observed on the T-Mobile network, where the SYN packet did receive the ACK immediately. So this is the kind of problem that can be analyzed in order to improve the app launch time on different networks. We also had a look, of course, at the rebuffering. and video storage or video streaming strategies. The buffering is also it's a very important KPI, the buffering and the quality of the videos, because there is like a real challenge that the social networks are trying to meet, where they want to optimize the amount of data they use versus the quality of the video that they stream. And so there's a lot of work around this in order to maximize the user experience, so minimize the buffering, maximize the MOS score, while minimizing the data tonnage, the data consumed by the phones. And so when we compared a little bit across the different applications, we detected that YouTube had a significantly bigger number of rebufferings on the different thousands of swipes that we performed. Facebook had 98% of sessions that were not affected by rebuffering, where YouTube had 93 to 97% of sessions which were impacted by buffering. And so we decided to dig a bit deeper to try to understand, to try to see if we could find the reasons to why this was happening. This is an example quickly of a buffering that we observed on YouTube Shorts. So you can see here, video is loading, the buffering will appear, and then the video finally starts. So these are the kind of buffering events that we measured. Again, when we looked at the network trace, well, first we were happily surprised to see that YouTube Short uses Quick to stream videos, which is, I mean, we've talked about it today, a fair share, which is a good practice in order to stream videos low latency, which is what they are trying to do. Because again, when users are, I don't know if you're avid watchers of short form videos, but people tend to just kind of swipe quite quickly. And so, pun not intended. But so here, so that was a good surprise. What we did detect though is that when we see the rebuffering on the screen, we had several requests that were shared across different IPs with a TCP RST ACK received, and we were very surprised to see that different source servers were responding. So we ran a quick stat on the source IPs that were used across the session. So that's for one scenario run. So it's 50 short form videos. And for 50 short form videos, you can see from the size of from the column number 4, the number of bytes received for each server. YouTube has like 30 different servers sending these videos. So it seems that they have multiple edge servers to stream these videos, which kind of makes sense from a storage perspective. They're kind of like sharing the load across different servers. But this lack of edge stickiness has an impact on the rebuffering events. Our guess is that this edge renegotiation causes some of the bufferings observed on screen. And so we checked other apps to see if that was standard behavior or just something that YouTube was doing. On Facebook, the same stat analysis revealed that it's not the case. If you look at the same fourth column, you see that Facebook uses 4, maybe 5 different servers. So each server is streaming about 10 videos, or if you look at the bytes, like 30 to 5, which makes sense. The stickiness of the edge it means that there is a lower strain on the application itself. We also had a look at TikTok. And contrary to Facebook and YouTube Short, who use Quick, we're very surprised to see that TikTok is actually using TCP. So we're quite surprised by this. And then it's a discussion that we can have with TikTok as to understand why. But maybe the fact that they are using their own CD, they're not using their own CDN, could be part of the answer here. That being said, the fact that TikTok stream in TCP does not have does not have a significant impact on the number of buffering. And so this highlights that it's great to have the network side, but it's also important to measure what's happening on the end user screen in order to understand what's the real impact for end users. And that's about it for the social network war, the balance that they're trying to find between data consumed and video quality and bufferings. Hope you had a good ride.